spend time on understanding the Lagrangian formulation. Oh, thank you.
Yeah, it wasn't recording.
Yeah, I know. I was not recording the MATLAB because I'll be posting the file anyway.
Oh, okay.
Yeah. But are you able to see the full board?
Now you can.
Okay, thank you.
You should be good.
Yeah, next couple of weeks we'll be doing the Lagrangian formulation. So what I want to do is I want to make sure that the jargon is very well understood. Okay, in the Lagrangian formulation you're going to have some terminologies that we will repeatedly make use of. So we want to make sure that we are all on the same page on that. Okay, let's start off. The Lagrangian formulation. There are two ways to approach this problem. Okay, there's the way that Lagrange used, which is using the principle of virtual work, which is what I'm going to do very soon. And towards the end of the semester, we will look at the other route, which is making use of the principle of least action or minimum action, which is using the tools of variational calculus. Okay? This is the variational approach. The variational approach is much more elegant mathematically, obviously, and you will see that. This is more dirty work, principle of virtual work. But the advantage, the greatest advantage of the principle of virtual work for us as engineers is that it will enable us to incorporate dissipative effects. The principle of Hamilton's principle, that's what it's called, the principle of least action or principle of minimum action. Hamilton's principle will come up with the Lagrangian but without the effects of the dissipative forces. That is only for conservative systems where friction does not play a role. For physics, people in physics who are doing quantum mechanics and so on, the variational approach is most useful. For us as engineers, this approach is most useful because we want to include friction. Friction is a part of our life. It's a part of many people's livelihood. All right. So before we do the principle of virtual work, we need to get some jargon down. We already seen a couple of configuration coordinates. We're just going to do some jargon, okay, configuration coordinate CCs. From now on, I'm going to be giving them a separate lettering. I'm going to call them as Q suffix I. Okay, so they're going to be called as Q suffix I, where I is 1, 2, capital N, where the QIs are the individual configuration coordinates. These are the total number of coordinates that are required to represent the configuration of a system at any instant in time. The total number of, total set of coordinates that represent the system at any instant. Previously, we would have called them as x of t, y of t, and z of t. I'm now going to be calling them as q1 of t, q2 of t, and q3 of t. No difference. Okay? These are all functions of time. Then constraints. We have visited this idea many times. Constraints. These are restrictions on the motion of the body. Motion of the system. And constraints can be written in several ways. Okay, can be written in two particularly different ways. One is F, J, J is the jth constraint. Fj of Q1, Q2, Q3 is equal to 0. So this is one way of writing the constraints. The other way is by making use of the velocities. Q1 dot, Q2 dot, Q3 dot of the configuration coordinates. Q1 dot, Q2 dot. So these are the two ways of writing constraints. And we're going to talk about these today. But before that, I have a few more things to do. Degrees of freedom. We've already revisited we visited this idea multiple times. Degrees of freedom is the number of configuration coordinates minus the number of constraints. That's the third idea. Okay. A, B, and C. And then what I want you to remember from now on is that this degree of freedom is just a number. Two, 3, 5, 7, something like that. Okay? The variable that you choose to represent the degree of freedom is going to be called as a generalized coordinate. Okay, so generalized coordinate are the minimum set of variables. That describe the system at any time. I'm going to call them as GCs. CC is configuration coordinate, GC is generalized coordinate. I don't have an algebraic lettering for them yet. Hang on to it. Okay. Now, how do we relate the generalized coordinate to the degrees of freedom? And this is where the nature of the constraints come into play. Okay, so the nature of constraints. There are two broad classes of constraints: holonomic constraints and non-holonomic constraints. Holonomic constraints, non-holonomic constraints. And the biggest battle in Lagrangian mechanics is figuring out which constraint is holonomic, which constraint is non-holonomic, and based upon that, your path of approach to the problem is greatly simplified, depending on which you choose, or which you identify. Holonomic constraints are position-based constraints. Position-based or integrable constraints, or integrable constraints. Non-holonomic constraints are velocity-dependent constraints or non-integrable constraints. Or non-position-based constraints. which just looks like a bunch of words on the board. So what is the math that will help us find out which of them is holonomic and which of them is non-holonomic is the following. Any constraint that can be expressed in the first form that you see here is a holonomic constraint. Okay? So any constraint, the holonomic. Any constraint that can be written as U1, U2, U3 as a holonomic constraint. And any constraint that's not holonomic is not holonomic. It's as simple as that. So any constraint that is non-holonomic not holonomic is a non-holonomic constraint. So far so good, right? Configuration coordinates, constraints, generalized coordinates, degrees of freedom. If I'm talking about constraints, there are two types. There are actually two more types which I'm going to talk about in a minute. Holonomic constraints and non-holonomic constraints. Any constraint that is holonomic can be written in this particular form. Or in more stronger mathematical terms, any constraint that is holonomic will pass the test for integrability. Any holonomic constraint of the form f of U1, U2 is equal to 0 will pass it has a name after a scientist called Pfaff. It will pass the Pfaffian test for integrability. And this is based on one of a very famous theorem in mathematics called the Frobenius theorem. Since I'm not a mathematician, I will give you a very shady proof. Okay? It's quick and dirty. That's all we need, right? Because we want to solve problems. We are engineers. Don't want to get caught in the math. There is enough math as it is. All right. So this is all it is so far. Okay. Now we want to define two types of systems based on the type of constraints. And they're called holonomic systems and non-holonomic systems. Okay? So holonomic systems are systems where all the constraints are holonomic. So holonomic system all the constraints are holonomic. Even if a single constraint is not holonomic, the system is non-holonomic. Okay, so if a system can have multiple constraints, right? If I take a 2D pendulum, the fact that it's in 2D is one constraint. The fact that its length is fixed is another constraint. So one constraint could be holonomic, the other could be non-holonomic, and the system is non-holonomic. If a single constraint, single system constraint is non-holonomic, the system is non-holonomic system. We are going to look at both of these things. The non-holonomic systems are very, very mathematically intractable systems. Okay? The equations of motion will be very messy. But we are going to do it. Especially the two seminal problems in dynamics, the rolling coin and then the spinning top. They're both non-holonomic systems. One can make the spinning top a holonomic system, but the rolling coin is still non-holonomic, and we will look at those equations over a couple of weeks. It will take a couple of weeks to develop the equation, and then you will simulate it. That's the achievement here, right? You just not only see the motion, but you can also physically simulate the motion. All right? So here are the things. Now, if I have a holonomic system, if our system is holonomic, then I can come up with a set of generalized coordinates. We can come up with a set of generalized coordinates which will be equal to the number of degrees of freedom, where the number of generalized coordinates is equal to the number of degrees of freedom, and this is what you have been seeing in this class so far. Theta of t, phi of t, r of t, all these things that we used to simulate the motion of a bead on a cone, or simple pendulum, one of these things. They are all generalized coordinates. And generalized coordinates are possible only for a holonomic system. And the greatest advantage of a holonomic system is if you are using the Lagrangian framework, you can completely ignore all the constraints once you prove that it's holonomic. They don't make a difference to your life, they don't appear in the equations of motion, because I'm not going to be looking at them anyways. And you'll see why and how. Right? If the system is non-holonomic, we can still come up with the number of degrees of freedom. That is, I can have 2 degrees of freedom for the system. If I have a rolling coin, I can have 3 degrees of freedom for the system. But I will not be able to come up with a set of independent variables equal to the number of degrees of freedom that will act as generalized coordinates. But what is, we cannot obtain a set of, here, set of independent generalized coordinates for a non-holonomic system. And I understand it is going to be very vague until we start looking at some examples. Okay, so just bear with me as we get down the words, right, and then we apply them to actual examples. And so very short sentence here. Holonomic system. Your equations of motion will be in terms of the generalized coordinates. if I have a non-holonomic system, I can still come up with the equations of motion. Obviously, I can apply Newton's law or Lagrange formulation to any of these kinds of systems. But the equations of motion will be in terms of the configuration coordinates. The equations of motion in terms of the configuration coordinates, which means that my final set of equations of motion should be in terms of the configuration coordinates, and I should also have the geometric information of the constraints appearing. So there will also be plus constraint info. That is, I have the system of equations, the equations of motion, but I will have more number of unknowns than equations in the non-holonomic system. The number of unknowns will be whittled down by saying, okay, here are the constraints now. So in tandem with the set of algebraic equations, which are the constraints, and differential equations, which are the equations of motion, you can solve the non-holonomic system, which makes it very challenging. Okay. So now let's take some examples, and maybe before that, one more line. Okay. You can also classify constraints in two ways. Let me maybe write it there. The word holos in Greek means position. Non-holos means non-position. That's where the holonomic comes from. Okay? The other classification of constraints is rheonomic and scleronomic. Rheos means you have heard of the term rheology, right? It's the study of slow-moving fluid. I take a bucket of asphalt and then pour it over the road. It's like slowly moving over time. That's the study of rheology. So, which tells you that if a constraint is rheonomic, then it's a time-dependent constraint. The word scleros in Greek means independent of time. So this is independent. This is a subset. Okay, so here is the final thing. Holonomic constraints can be rheonomic or scleronomic. Non-holonomic constraints can be rheonomic or scleronomic. Okay? The holonomic constraints can be time dependent or scleronomic. And likewise, non-holonomic constraints can also be that, right? Can also be rheonomic and scleronomic. Okay, so now let's start looking at some simple examples. Two examples for today. This is my x-axis, y-axis, and z-axis. Let's say that I have a particle on an xy plane. Well, it's on a constant z plane, say. Here is my plane and the particle. And this is Z naught. Okay, so for this particular example, I want to write down the configuration coordinates. I want to write the constraints. I want to write the constraints in its functional form to see if it can be classified as a holonomic or a non-holonomic constraint. And we will soon realize that it is difficult to take a given constraint and write it in the functional form just by looking at it. So we need something deeper, which is the test for integrability. Okay? All right. How many configuration coordinates? Three. When you think of configuration coordinates, you are not thinking about the constraints. If there are no constraints, what would this particle need to know to see where it is? X of t, y of t, z of t. Okay? But I'm not going to write it that way. I'm going to say that so configuration coordinates x of t, which I'm going to write as q1, y of t, which I'm going to write as q2, and then z of t, which I'm going to write as q3. Okay, so three configuration coordinates. Constraint. What are the constraints?
Z equals C naught.
Z is equal to C naught is the constraint. That's probably the only one constraint here. So I'm going to say J is equal to 1 is the first constraint. And that's Z is equal to Z naught, but I don't want to write it in terms of Z. I want to write it in terms of my QIs. Okay, so this essentially tells me that Q3 is Z naught or Q3 minus Z naught is equal to 0. Or I can write it in the following manner. Q3 minus Z naught is equal to 0 can be written as 0 times Q1, right? 0 times something is 0. 0 times Q2, same result. 1 times Q3. 0 times some time 3 minus 0 is equal to 0. Z naught is some constant. Now, if you want to make your life better, you can say Z naught is equal to 0. Doesn't make any difference to us. And my question to you is this a holonomic constraint? Remember, what's a holonomic constraint? I can write it as a function of the configuration coordinates, the position coordinates. Okay, so is it a holonomic or a non-holonomic constraint? It's a function of Q1. The coefficient accompanying it is 0, doesn't matter. The function of Q2, it's a function of Q3, it's a function of time. This is a constant, it is just a scaling parameter, does not affect my life. So this is indeed a functional function of position. Okay, so this can be written as the following. The first constraint, right? So there's only one constraint, so F1, Q1, Q2, Q3, and T is 0. So just by inspection, you can say that this is a position-based constraint, and it makes common sense, right? I mean, I'm restricting the motion of this to lie on a particular plane, so its position in the z direction is restricted, and that's the significance of a position-based constraint. So this is a holonomic constraint. So Q3 is equal to Z naught is holonomic. If the system is holonomic, I can come up with, first of all, what are the number of degrees of freedom? Is 3 minus 1, right? I have 3 configuration coordinates, I have 1 constraint, so 3 minus 1 is 2. I have 2 degrees of freedom, and because the constraint is holonomic and this is the only constraint, the system is holonomic. One constraint which is holonomic. Which means the system is holonomic. And if the system is holonomic, then I can come up with generalized coordinates equal to the number of degrees of freedom. We can come up with generalized coordinates where the number of generalized coordinates is equal to the number of degrees of freedom. And what do you think could be the generalized coordinates? Q1 of t and Q2 of t, absolutely. So this is a situation, a special situation where the generalized coordinates are coincident with the configuration coordinates, Q1 and Q2. Okay, so, or if you are really going for a fancy effect, I could also choose an R and a theta, if you want. That could also be a choice for my generalized coordinate. Okay, so there are 2 choices here. I could choose x and y, obviously. X of t, which is q1, y of t, which is q2. So this is one choice. And then another choice could be r and theta, or r and theta, which are also 2 in number, because I have 2 degrees of freedom. And so, the important thing here, the generalized coordinates can be the configuration coordinates, but the opposite cannot happen. The configuration coordinates in a non-holonomic system cannot be called as the generalized coordinates. Okay, so there is this mismatch here, right? Generalized coordinates can be chosen to be one of the configuration coordinates or 2 of the configuration coordinates, but I can't do the same thing. I don't have a notion of a generalized coordinate or a non-holonomic system. Alright, so that's one. Let's maybe do one more quickly. Let's do a wheel rolling without slip. 2D. Okay. X-axis, y-axis. Fixed radius r. How many configuration coordinates? Two, three. Let's see. Three. Nobody wants a bit higher.
I'll go 4.
4. Let's go with 4. You see why? Once again, when you're thinking about configuration coordinates, forget the constraints. Forget the constraints that this is sitting on a 2-dimensional plane. Okay, so the 4 configuration coordinates are, I need 3 of them to specify where the center of mass is, and I need a rotational variable to specify where it is or how far it has traveled. Okay, so there are 4 configuration coordinates, and they're going to be x of t, y of t, z of t, theta, and I'm going to call them as q1, q2, q3, and q4.
Sean, question.
Yes, yes.
So why don't you need the angles in about the x and the y?
Well, yeah, in reality, I should have 6. Yeah, you're right, yeah. Yeah, that's great, yeah. Absolutely. That's right. Yeah. And there is some side of it, yeah, absolutely. Why not, right? Yeah. This is Q5. Q6. So this is a full-blown rigid body. Fantastic. Yeah. What are your constraints? Let's say that the z-axis is coming out, this is z is equal to 0. This plane, z is equal to 0 plane, right? So I can say that the first constraint, look at this, I'm now going to start writing them in terms of the derivatives. Okay, a few more minutes and then I'll write the constraints and then we'll come back in the next class to complete. Okay, so z dot is 0. Okay, that's constraint number 1. Then I have how many more constraints left? What could be my other constraint? I gave the easiest one here, so
Is it rolling without slip?
it's rolling without slip, so that's another constraint. Let's say that it's rolling without slip. Okay. That's constraint number 2. Of course, we have to write it in an equation form. What do you think would be the equation for the rolling without slip? So planar body. Yes.
Would that be that theta is related to r and x?
Theta is related to x. Yeah, r is a constant, but you're right, theta is related to x. So x dot is r times theta dot, right? The center of mass, the motion of the center of mass is corresponding to the circumferential travel as well. So x dot is r times theta dot, or q1 dot is r times q3 dot, q4 dot, sorry. What other constraints do you have? Yes?
The y coordinate of the center is always going to be r.
Fantastic. So y coord is fixed. So q dot of q is 0. Y dot is 0, or y is equal to r. This essentially tells me that y dot is 0 or y is equal to r. So this is j is equal to 3. Any more constraints? I'm telling you this is two-dimensional motion. Yes.
Is it psi dot and phi dot? Is it?
Yeah, therefore that will be 0. Yeah, absolutely. Those are my fourth and fifth constraints. Phi dot is 0, so Q dot phi is 0 and psi dot is 0. Q dot 6 is 0. You see that this becomes very boring after some time because you have to write down all of these things. And so we have to come up with a quicker way of doing these problems. Right? And we will see it. So I have 5 constraints, 6 configuration coordinates. I should represent this as 6, not 4. And so the number of degrees of freedom is 6 minus 5, which is equal to 1. And you obviously know what the degree of freedom here is, right? It's going to be theta or x. Okay? But we will see how that works out. Okay? In the next class I'll come back. I'll start off at this particular step. And then I will take a 3-dimensional case of the same problem, where it is still rolling without slip, and we will see what changes between the two. Okay? Thank you.